the periodic table is the next lesson that we're looking at. By the 1780s, chemists wonder why some elements such as oxygen were gases while others such as gold were metals, right? Solids. Right? By the 1860s, the list of known elements had grown to about 63 elements. That's what made up of the some of the most primitive periodic tables. It was unknown whether there were hundreds or even thousands more of these elements that were yet to be discovered. As it's obvious, right, to the periodic table, there's way more than 63 elements on that periodic table. So we know that there have been more. We don't know if there's even more that have yet to be discovered. Many chemists continue to search for a unifying pattern among the elements. So if we look at that periodic table is organized in its most appropriate fashion. Right? But before, they didn't have it in this order. The order that you see it, the way it's drawn, we're thinking, well, why isn't it just listed, a whole bunch of them? Right? But they're shown in an order that will help you identify certain properties. In 1867, Russian chemist and teacher Dmitri Mendeleev found the pattern scientists have been looking for. He gathered information based on properties such as estimates of the masses of the atoms of each element, their color, their density, melting point, and what each element did or did not react with. Right? So he really had nothing. So he had to figure out a way to try to distinguish one element from the other and see, are there patterns? Are there similarities? Can I put this periodic table in a way that will help me better understand the properties of even other elements? So was there a commonality between various atoms in the periodic table? So he wrote these things on little cards, right? And he kind of separated these cards from one another and started to group them based on things that he noticed that were similar to one another. So here in this diagram here to the left up at the top, we have sodium, and he broke down the things he knew about sodium. Its atomic mass, the color, density, its reactivity. Right? So Mendeleev then sorted the cards into rows and groups based on similarities in the element's properties. Right? So he had a whole bunch of these cards, and he sorted them out. Right? So a whole bunch of these cue cards that he sorted out, and he put them together with other things that were similar. Right? Oh, okay, maybe color, they're all gray. Okay, so all these together. Oh, these are reactive with water, but these aren't. So we're going to separate them together. So he was trying to figure out a way to show these elements together. So in Mendeleev's table, all the cards representing metals ended up on one side, and all the non-metals ended up on the other. Right? He placed the metalloids in the middle. Right? Just like we see it in the periodic table, in our modern periodic table. So very similar. So that's how it's slowly coming to play. He goes, okay, well, all the metals, we're going to put on this side. All the non-metals, we're going to put on the other side. Well, we've got these others that are similar to both. We're going to put those in the middle. That's where I think they belong. And then he saw, okay, certain reactivities that existed amongst the metals. Certain reactivities that existed amongst the non-metals. And he put those together. Most of the elements that were gases at room temperature were grouped together, right? If they're gases, they're all gases, so they all got to be similar properties. He grouped sodium, lithium, and other metals that reacted violently with water together. Now notice these two, sodium and lithium. So you can imagine that he had them one on top of the other, right? Because they both exhibit the same violent property when exposed to water. He left gaps in his table if he could not find an element with the right properties to put in a column. So that was the possibility that there were other elements that have yet to be discovered that fit in those gaps. So we have now the modern periodic table. This is the modern periodic table that we know of today. The periodic table is a chart that places all the elements in rows, right? The rows are called periods. So here's the first row, second row, third row. We're not going to call them rows. We're going to call them periods. That's very important to know. Okay, and the columns as groups. So here's a column, right? Here's another column, another column. Okay, these are not columns. We're going to call them groups. So please make sure you know the proper terminology. So please be able to identify which are the periods, which are the groups. And you're going to notice that the periods are numbered here on the side, right? 1, 2, 3, 4, in sequential order. And so are the groups 1, 2, 3, 4, 5, all the way to group number 18. Some periodic tables might have them in Roman numerals with the letter A and the letter B. You treat them as 1, 2, 3, 4, all the way through group number 18. So that's how I want you to look at it for now. Okay, because that's going to come in handy later on when we're trying to label the atom and the parts of the subatomic particles that make up each atom. So, the atomic number. The atomic number is the number of protons in an atom of an element. So if you look at the numbers on the periodic table, you'll notice that the numbers go in order. Here's 1, here's 2 on the other side. Here's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get the idea, right? So they go in sequential order. The number that goes in sequential order, these are known as the atomic number. That number tells us how many protons exist. So if you look at the periodic table, hydrogen atom has the atomic number 1, which means it has 1 proton. Helium, the other atom, has an atomic number of 2. That means it has 2 protons. Don't worry about this number right now. Right? So we know protons carry a positive charge. Because none of these atoms exhibit a charge associated with them, if we have 2 positive charges, we must also have 2 negative charges associated with it. We've got 1 positive charge here in the nucleus. We've got 1 negative charge to offset the no charge. The lowest atomic number is 1, which is the atomic number of the element hydrogen. Every hydrogen atom has 1 proton in its nucleus. That will never, ever change. So the atomic number tells us the number of protons. It will never change. So hydrogen has 1 proton. If you find an atom that has 2 protons, find the atomic number that has 2. Right? That's what the element we're looking at. Right? So the number of protons always match the number, the atomic number. So as we said, the next element in the periodic table is helium, has the atomic number 2. All helium atoms have 2 protons. The third element on the periodic table is lithium. So lithium will have 3 protons. The fourth element is beryllium. So let's look at a random one. So look at phosphorus. Right? So look at phosphorus on the periodic table. It's with the symbol P. It has the atomic number of 15. So phosphorus has 15 protons. Atomic number increases by 1 with each consecutive element. So as we go from left to right, like we read, right, like the English language is in terms of reading, go from left to right, it goes 1, 2, and then down to the next period, 3, 4, 5, 6. So it goes in order. The atomic number always goes in order. So that atomic number, as we said, number of protons. This increase continues through the entire table until the atomic number is well past 100. All right? So as of 2009, the highest possible atomic number is at 118. So your periodic table is most current if it has up to the atomic number of 118, which means that that atom contains 118 protons. If you do not have 118 atoms in your periodic table, or elements in the periodic table, then you've got one of the older versions of the periodic table. Other information that can be found on the periodic table. Within each boxed element on the periodic table usually shows the element's name, the symbol, and the atomic number. Okay? So, name, symbol, atomic number. Those 3 things should always be there. Sometimes you might not see this, the name, right? Sometimes you might see an even simpler version. But the atomic number should always be there. There are other bits of information that are very useful to us that can be found on the periodic table. So it's really important that you get a good periodic table. If you go onto my my website, my eClass website, you can download a decent periodic table if you've lost your agenda. So you should all have a decent periodic table in your student agendas. But if you don't have one, if you lost your agenda, you can always download it from the eClass website. Okay, so other bits of information that can be found in each one of these boxes are as labeled. We have the atomic mass, right? So the so-called weight, okay, and in quotations, weight, right? We don't really use it in terms of weight, but we refer to it as mass. But that's kind of like, you know, the mass of this atom. Okay, and you'll notice that it's in decimal form. A lot of times, what I want you to do is I want you to round it off to the nearest whole number. So as 56, when you do certain calculations, and I'm going to show you. Don't always do that, right? Don't always do that. You don't need to always do that. But when you're doing a certain calculation, I'm going to show you guys later, round it to the nearest whole number. And then another thing you'll find is the ion charge. So it just tells us how many electrons can be gained or how many electrons can be lost by that atom to reach a stable state. So for this one, iron can be a +3 or a +2. So let's look at atomic mass. Atomic mass is the average mass of an element's atoms. One thing you're going to know is that each atom, okay, each element has what we call isotopes of themselves, right? So it's never really the same type of iron, right? But they all have the same atomic number. Okay, don't worry about the term isotopes yet. We'll talk about that in a later chapter. But that's why we have a number that's in decimal form, because there are various masses of iron that we use. We might use one type of iron, but all of them will have 26 protons. The difference, as we're going to see, is in the number of neutrons, right? And ultimately leading to a different atomic mass. But don't, like I said, don't worry about that just yet. Now, units used for atomic mass is AMU. Okay, AMU. That stands for atomic mass units. So, 55.85, right? If we want to put a unit to it, you know how we put centimeters, meters, kilometers, hours, seconds, grams, right? So there are units that are associated to atomic mass, and we use AMU. So the atomic mass of iron is 55.85 AMU. That's the units that we use. Right? So the atomic mass of hydrogen, if you look at the periodic table, is 1.01 AMU. We don't put the AMU, but you should know that those are the units that we use for atomic mass. Right? What does that mean? It means that iron is 55.85 times heavier than hydrogen atoms. So whatever that atomic mass means, it means it's that many times heavier than hydrogen. Right? We're always referring to hydrogen because hydrogen is the first element on the periodic table, first atom on the periodic table. Ion charge, and we're going to talk more about ion charge in the later chapters when we're comparing the difference between an atom and an ion. So now, the ion charge is the electrical charge that an atom takes on when it loses or gains electrons. So an atom or a group of atoms that has lost or gained electrons. So only if they've done this, okay? Only if they have lost an electron or two or more, or have gained an electron, then the atom is no longer called an atom. An atom actually becomes an ion. So magnesium atom can become a magnesium ion if it gains or loses electrons. Okay, we'll talk about that again, like I said, at a later point. Okay. Now, metal atoms can lose electrons in certain situations. Electrons have a negative charge, as we've talked about in previous chapters. So an atom that loses electrons becomes a positive ion. So here we have iron. We've lost 3 electrons. So because we've lost 3 electrons, we have a charge of +3. We can never, and I repeat, this is really important for you to know. you can never lose protons. Because remember, you can never lose protons because protons equal the atomic number. If you lose a proton, it will not tell us the atomic number. It will not tell us the appropriate atom that it really is. Right? So, helium has an atomic number of 2, which means 2 protons. It cannot lose any of those protons because then it's no longer helium. Okay? But we can, I repeat, we can lose electrons. Electrons, because remember, that's the outer part. Right? We've got our nucleus, and we've got electrons that surround it. Right? Here's where all the protons lie, in the nucleus. So the only thing we can either gain or lose are these electrons that are surrounding our atom. So, in this example as we have here, right, if an iron atom loses 3 electrons, it becomes the ion that has the +3 charge. If it loses 2 electrons, it becomes an ion with the +2 charge. And if you look at that box that we saw before, we saw the +2 and the +3. And if you look at your periodic table, you'll find iron like that. And that's what it means. When you see the +2, it means that we lost that many electrons. If it says +3 or if it says +1, it means we've lost that many electrons. Now, if you look at all the metals are the ones that actually have this positive charge. If you look at the non-metals, they all have a negative charge associated with them. That means they have gained electrons. And again, we're going to talk more about that in a later chapter. So, elements with atoms that can form similar ions are grouped together in the periodic table. Metals generally lose electrons and become positive ions. So, if you look at the periodic table, you'll see that the metals all have positive ions that are associated with them. It means metals will lose electrons. When metals lose electrons, they become positively charged, right? And these positive ions are called cations. So we think of the T as a plus shape, right, for positive. Non-metals, so if you look at the opposite side of the periodic table, they gain electrons. So non-metals gain electrons, and so because they gain electrons having a negative charge, so they become negative ions. So these negative ions are called anions, and we're going to talk more about that and think of the letter N for negative, right? Anions, negative charge. So what kind of an ion? Negative ion. Cation, what kind of ion is it? A positive ion. So use that as your reference point. Some elements do not form ions. So an example, helium does not form ions. So if you look at group 18, it is the column at the very, very right of the periodic table. It starts off with helium, neon, argon, krypton, xenon, radon. All of these do not form ions, right? Because these are what we call noble gases. These noble gases are in its most stable state. For these elements, no ion charges are shown in their squares in the periodic table. So you'll notice that those are the only elements that really show no charge. You'll see some of the metals also don't show them, but you know, we'll talk about that at a more senior level. Periods and chemical families. The periodic table has 7 horizontal rows, right? And as we said before, the rows, we're not going to refer to them as rows, we're referring to them as periods, right? There are 18 vertical columns. As we said, we're not going to call them columns, we're going to call them groups, and some actually are called chemical families. And here are 4 certain chemical families. Right? We've got group number 1, we've got group number 2. If we look over on this side, we've got group number 17, and the final group at the opposite side, group 18. Okay? So group 1 are the alkaline metals, group 2 are the alkaline earth metals, Group 17 on the opposite side are called the halogens, and group 18 are called the noble gases, and these are the most stable of them all. The elements within a group share certain physical and chemical properties. Each group has its own number written at the top of the periodic table. That's the group number. So, example. The element carbon is in group 14. It doesn't have an exact name, but if we look at carbon, it's the first atom in that group. So we call it the carbon group. Okay, so we refer to it by the first element in that row, or sorry, in that column. Right? So group 14 can also be referred to as the carbon group. But the most important groups to be able to identify are those four that I showed you. The alkali metals, the alkaline earth metals, the halogens, and the noble gases. But don't worry, I'm going to show you them individually, and I'll show you what those names are written. So, and here they are. Special groups of the periodic table. Alkali metals, alkaline earth metals, halogens, and noble gases. So, group 1, group 2, group 17, and sometimes we might refer to it as group 7, as we're going to see. And the noble gases are group 18, and sometimes we'll refer to them as group 8. And this hint will help us later on when we're drawing actual atoms. So let's look at each one of these chemical families, starting with the alkali metals. Notice which alkali metal is not drawn there, or which atom is not drawn here. Hydrogen. Even though hydrogen is in the same group, it is not considered an alkali metal. Hydrogen is an element on its own, and if you notice, some periodic tables will actually separate it a little bit from the periodic table. So, some similarities between alkali metals. Obviously, they're group 1. Notice, no hydrogen. They're metals, so they're malleable and ductile. They have low melting points. They all melt below 170 degrees Celsius, a temperature that is easily achieved by most ordinary kitchen ovens. Very reactive with air and water. Okay, so they're violently reactive with air and water. And as we move down, they become more and more reactive. They all consist of one valence electron. This is going to be really important, but we're going to talk about this term later. Okay, but notice here, one valence electron, group 1. There's going to be a hint there, as we're going to talk about later on. Easily loses that one valence electron. So remember, if we lose electrons, we form cations, which contain a positive charge. So if we lose one electron, we will all have a +1 charge. And notice, they're all labeled with a plus, right, or +1. So all alkali metals can lose that one electron that is considered the valence electron. Like I said, we'll talk about that later. So, a few differences. They increase in density as we move down the group. So as we move down, the densities actually change. The elements get softer and easier to cut as we move down. The lithium's melting point is 170 degrees, while potassium is 64. Cesium's melting point is 28 degrees Celsius, which means the temperature, right? The temperature decreases for its melting point. The melting point decreases as we move down the periodic table. Next group, alkaline earth metals. And we're not going to compare similarities and differences, right? The alkaline earth metals is group 2, right? They're also metals, so they're malleable, ductile. They're not as reactive as the alkali metals are. They consist of 2 valence electrons. Notice that 2 now, group 2. Okay, well, like I said, a hint. 2 valence electrons that actually can be lost. They usually give them up. So if they lose electrons, as we said all metals do, they form cations. Okay, a couple of examples here. We've got magnesium and calcium. And notice the charge if you've got a good periodic table. +2 for all of these alkaline earth metals. Halogens, right? So we're over at group number 7 or 17. So we're second last column or second last group on the periodic table. They are non-metals. They have a noticeable color, they're very reactive, and they can be used also as disinfectants, have a tendency to gain electrons, okay? So they can gain one electron. So because they're gaining an electron, right, they become what we call anions. They form anions, right? Notice how they all have a -1 charge because they have gained one electron. Another thing that's not shown here, they all have 7 valence electrons. 7. Right? As I said, you're going to see this hint, right, as we're talking about. Let's look at the differences of amongst the halogens. So, color intensity grows as we move down. So, as we have here, in the first one, we've got fluorine, we've got chlorine, we've got bromine, and we've got iodine. Okay, so as I said, as we've noticed that there is a distinct color amongst the halogens, and that the intensity of the color actually increases as we move down the periodic table. Their melting points also gradually increases as we move down. So if we look at fluorine, the temperature in which it melts is at -219 degrees Celsius for fluorine. But if we go further down to iodine, right, that temperature goes to 113 degrees Celsius as the melting point for iodine. And finally, the noble gases. So similarities include the fact that they're in group 8 or 18. Okay? They're very stable elements since their valence shell is full. And we refer to this as an octet rule. I'm introducing the term, but we will talk more about it in the upcoming chapters. So, and we think of, and if we want to break down the term octet, think of 8. So their valence shell full, with the exception of helium. It's still full, but it's not going to fulfill that 8 valence electrons rule. Does not bond with anything, so you'll never see helium or neon or argon bonded with oxygen or with chlorine or with anything else. They exist as its own entity. All exist naturally as colorless gases. These elements will glow with bright colors if an electric current is passed through them. So we think about, neon lights, right, in the different colors, right, that bright colors. So whenever we look at, bright colors, when we think of xenon, right, the xenon lamps we can find in cars, right. So keep that in mind. They exist on their own, right. These are just a couple of examples. Now, in terms of also the similarities and the idea of the 8 valence electrons, or the full octet, right? You said valence shell is full. So it's full with 8 electrons. And as we've said in all the previous examples, notice 8 with the 8 from 18, right? And that's why we'll refer to it as group 8 or group 18, right? With the exception of helium. Helium is the only one that number of valence electrons is 2 valence electrons. Okay, so please remember that this one is the only exception to that rule. So differences, the density of the gases actually increases steadily, moving from helium through to radon. So if we were to use these gases to blow up balloons, right? The one that will rise the highest would be those filled with helium, right? Then with neon, right, not as dense, or sorry, is more dense than helium, so it will also, can use to keep a balloon up in the air, but it won't rise as quickly as it would for helium. And as we move down, of course, that rule still applies. So the density, and as we've talked about in terms of density previously, density is equal to the mass divided by the volume. Right? So this density is going to increase as we move down, right? Which means the most dense would be lower down here, and the least dense elements would be helium.